welcome to our first meetup that we're holding at an APAC-friendly time. Peter's been going very, very deep within the blockchain space, more in a sort of R&D capacity for a number of years. Throughout a lot of this time, he's been very focused on these cross-blockchain technologies. But he comes from a cryptography background as well. So it's one of those nice things where you've got someone who's got really deep industry expertise and then kind of brought that across to the blockchain space as well. So it's always fascinating to hear what he's been up to, and going to pass over to him now to do his talk.
So today I'm going to talk about general purpose atomic cross-chain transaction protocol. And so it's a blockchain layer 2 core graph commitment scheme that allows you to do atomic cross-chain transactions. And so I guess I really do need to unpack that. But before I do, please note that there's a paper on arXiv which explains it in great detail. There's an open source repo as well, which you can have a look at too. So blockchain layer 2, what do I actually mean by that? So what I mean by that is that you can think of the blockchain platform. So the Ethereum client is blockchain layer 1. And so you could think of like your TCP/IP network being, say, blockchain layer 0 if you have a layered stack. And so layer 2 are these essentially smart contracts that sit on top and the off-chain software which is associated with them. So what this means is that this is a technology that doesn't require changes to the underlying Ethereum client to work. You just have some contracts on chain and some off-chain software as well. Core graph commitment scheme, by that I mean that you have a set of function calls where one function calls another function and that function can call other functions as well. And what you do is you commit to executing that core graph. So you work out what values you're going to be passing in and you work out what changes you expect to be making, and then you commit to that. And then assuming what you commit to is what you actually execute, then it's all going to work fine. So atomic is a very important feature. So a lot of cross-chain protocols, you have something happen on the first blockchain, the source blockchain, and on your target blockchain, you just fire an event across, and it might end up there, it might get executed, it might be able to be executed, or it might not. And so you have no way of knowing. And on the destination chain, you have really no way of knowing that the thing on the source chain actually happened. And so this scheme allows you to be sure that you either update both chains or you end up discarding the updates on both chains. So it's a way of ensuring you have consistent state across the chains. And most of the cross-chain protocols that exist are just across 2 chains, a source and a destination, whereas this protocol allows you to go across many blockchains. And and again, reiterating, function calls across blockchains. And so before I dive in though, I think it's important to state very explicitly that this protocol is going to work on any EVM-based blockchain. So mainnet, so the public Ethereum blockchain, public test nets. It'll work on consortium blockchains, so private permissioned blockchains, or any other EVM-based blockchain that exists. And the technology should be able to work on any blockchain that supports contracts and events, so Hyperledger Fabric, Corda, and a whole range of platforms. And the intention certainly is to expand it out to be a protocol to bring together all of the blockchains. Another thing to think about is that, so Bitcoin, it was all about transferring value, whereas Ethereum, you can transfer value, but it's also about the business logic, the smart contracts, deploying a contract, calling functions to do some sort of business logic. And similarly, you can think of atomic swaps as just switching value between 2 chains, whereas cross-chain function calls allow you to do that as well, but also allow you to do something much richer, which is calling business logic across blockchains. So I'm going to introduce an example, and then I'm going to talk about CrossChain Consensus, the actual protocol itself, the implementation, security, and where things are going. So imagine this trade finance scenario. you have a wallet blockchain with a contract on it, which is essentially a multi-sig wallet. And so people who are involved in the overall transaction say, yes, the goods have arrived at the destination and we need to pay for them. And so you sign, and then you maybe the members who is actually signing off is private. And so that might stay private. So the wallet blockchain might actually be on a private consortium network. Whereas the terms blockchain, maybe it needs to be shared with some sort of government regulator. And so the actual terms of the agreement, the business logic behind that need to be public. You might have a price oracle blockchain, which has a contract on it, which you are certain that that is the current price for the goods that are being shipped. And so you might have to pay for access to that blockchain, or maybe it's a public one. You've then got the finance blockchain and the logistics blockchain, where you've got the people involved in finance, the banks, the vendors, and then the logistics, you've got people involved in the actual supply chain logistics. Now, you could argue that all of these contracts could be on the one blockchain, but in reality, invariably, the logistics people are completely separate to the finance people. You will have some crossover, but the consortium members will be different, and they will not want to be on the same blockchain because they'll have information which is private to their group. So hence, you do need to have some separation. So cross-chain consensus. So something to think about when you're thinking about these cross-blockchain protocols is that not everyone is going to be on the same blockchain. So look at Enterprise 2. It doesn't have a node on blockchain A. So if something happens on blockchain A, somehow or other, Enterprise 1 and Enterprise 3 have to sort of convince Enterprise 2 that that's really happened. And similarly, say if there's some update that happens on blockchain C, Enterprise 3, before it commits its changes to its blockchains, it wants to know that that's really happened. And so again, you need to prove that stuff's happened on remote blockchains. And so that's what cross-chain consensus gives you, an assurance that something's happened on a remote blockchain. Come on. Okay. And so the system that I've put together relies on Ethereum Events. And so if you look at the code we've got on the screen here, you've got an event defined, say start, which takes some parameters. And you've got a function, which is just some normal Solidity code function. And it calls that event in the middle of the function. And so what that means is that if you call the start function, it'll emit that event and then programmatically. So the parameters that are emitted in that event are going to be based on what the code says. And so that means you can programmatically generate information. And so why this is important is that, say in Ethereum, you have blocks, and in the block header, you have the transaction receipt root. And then you have a modified Merkle-Patricia trie, which is that, that thing just there. And within each of them, the bottom element is the actual transaction receipt. And within that, you have event logs, and the event logs contain the event information. So the address of the contract that emitted the event, the topic, so essentially what the function was that emitted the event, and the parameters of the event. And so you can imagine a system where you have the transaction on the source blockchain or that's submitted to the source blockchain causes an event to be emitted. And then somehow or other, using some sort of relay node, you have a transaction on the target blockchain. You give information, this trust information, and you submit a transaction, and then that gets that trust to the target blockchain. And then maybe you can use the Ethereum event combined with that trust information to prove to the target blockchain that something's happened. And so the thing, of course, is how do you trust this trust information? And so one approach is direct signing. And in direct signing, what you do is you have a set of validators who have their public keys or their accounts registered in a registrar contract on the target blockchain. And you have events that are assigned by a threshold number of validators on the source blockchain, and they were trusted by virtue of the signatures can be verified. And so what this looks like is this. You submit a transaction on the source blockchain, you emit an event as part of that function call, and then you have relay nodes, and they cooperate together to have a threshold number of them sign the event. So they essentially, each one would have the event, and when it deems the event is part of a transaction which is final, it fires that off to the other relay nodes. And then a user gets that signed event by asking for it from the relay nodes, and then it submits a transaction to the target blockchain that has the event in it and the threshold number of signatures. And then because you've submitted it with those signatures, it'll be trusted on the target blockchain, and then you can do something with that. And so, the advantage of this sort of system is that you only need to be signing the events that you do actually want to have end up on that target blockchain. You're not having to send some sort of block header all the time. And another thing is that you note that the user is the one who's submitting those transactions on the target blockchain. So if, say, your destination chain was Ethereum mainnet, and you're going to have to pay, say, $30 per transaction, then who's actually paying for the transactions is pretty important. Another way you can do it is block header transfer or transaction receipt transfer. And essentially the idea here is that you transfer the block header, and then you're able to prove that an event has occurred using a Merkle proof. So in this scenario, again, you emit an event, and then you have the relay nodes. They actually look for the block header, and when they feel that a block's final, they then create a threshold signed block header, which they then submit to the target blockchain. And then any user can submit the event along with a Merkle proof to the target blockchain, and then the event will be trusted because the block header is trusted. And the advantage obviously is that you only have to be putting across, so signing and then submitting one transaction per block to actually have it trusted. But then you might be signing and transferring a whole heap of block headers that are not needed, which would be a waste. There's also a methodology called SPV, so simple payment verification, which is used by BTC Relay. And essentially there you're using the proof of work difficulty of the source blockchain. And I won't go into that in detail, but it's similar. The actual words in these slides that you can see later tell you all you need to know. And the aggregation blockchain is a similar sort of thing. You have multiple source blockchains. They fire essentially the block header to the aggregation blockchain, and then it aggregates essentially the root hash of the block header, and then you then fire that across to all the target blockchains, and then you essentially have a Merkle proof of that the event belongs in the block header, and then another one to prove that the block header is part of the overall aggregated block header. And that's also got some advantages and disadvantages, but the big thing to think about with all of this stuff is finality. So it's all very well and good to transfer an event or a block header and an event across to a target blockchain, but if you're using proof of work, it's not instant finality, it's probabilistic. And so you need to have something like 10 block confirmations on Ethereum to be sure that you're going to have a block nailed in and final, assuming a 30% mining power attack, and and a 1 in a million chance. So you've got to have a look is, what's the probability of a 30% mining attack? You need to probably be investing about $500 million to do that. So it seems unlikely, but still 10, block confirmations is, around about right. And the big thing to think about then is that before you could transfer that event, you needed to wait those 10 block confirmations to make sure it was final. If you're on a consortium blockchain, though, you can have something called instant finality using something like IBFT2, where essentially once the block is minted, then it's final. And so, yeah, and that's already said that. So having a look at it, you've got these different methodologies, and I think probably for most systems, the basic direct signing is actually the way to go. It means that the validators are signing each event, but it does mean that the users are paying for it. And as well, it will reduce the actual latency required, which is important. So the rest of the talk assumes that you're going to use a consensus mechanism, and it doesn't prescribe which one you use. And so, so let's go through assuming that you have consensus, the actual protocol itself. So the first thing you need to do is simulate the call graph. And so you need to essentially work out what the expected parameter values are for the entry point functions for the contracts of each blockchain. So essentially you may need to get fetch state to be sure of what you've got, what the current state is, because that may affect the actual values that need to be passed into function calls. And so if you look here at the example that we had, then if you were on that logic blockchain, you might have that shipment function, and you can see that you're going to need to have that seller, the buyer, and the quantity, those parameter values determined ahead of time. And so you're going to need to be looking at, all right, well, what is the value that is returned by the call to the price oracle blockchain? And because then that then determines what the cost is, and the cost is then passed in as a parameter to the balances blockchain. And yeah, so as it says there, the simulation will determine the value by returned by get price. So all of this is brought together in what's called the cross-blockchain control contract, and it's got these entry point functions, and essentially you're using the cross-blockchain control contract as a proxy for actually calling the real business logic code. And so what you do is something along the lines of what's shown in this example sequence. So you have a start function call, which will essentially commit you to what is the call graph. And then you have segments which execute the individual parts of the function call. And then you go incrementally up the call graph from the bottom of the call graph towards the root of the call graph. And then you execute the root. And if all of that's executed okay, then you're going to be able to commit any changes that you've made. And so that has said that quite quickly, but if you're trying to unpack this, so for that start function, what you do is you pass in a timeout value and the call graph, and the call graph's in a special format so that you can see all of the function calls that are going to happen. And then the big thing that this function does is it emits a start event. And that start event then is really saying, all right, this is what's going to be executed. And then you have segment function calls. And so what you're doing is they may be partway up the call graph. So they may have values returned from subordinate calls. And so they'll be passed in as signed event information from the segments. As well, you're going to have this start event is passed in. And so that had the call graph. And then you have this call path value. And the call path value tells you where you are in the overall call graph. So essentially, it tells you what part of the call graph we're currently executing in this segment. And then segment events are emitted, and they tell us, what call graph was executed against, what part of the call graph was executed, and importantly, what the return results are and what locked contracts exist. The root call is used to do the root of the overall cross-blockchain call. And so it has the start event and any segment events as parameters. And it then commits that root event saying, should we discard the results of the updates, or should we commit them? And it'll commit any updates on the root blockchain itself. And if the overall call is timed out, then it'll fail as well, and it'll indicate everything needs to be rolled back. Signaling functions are used to unlock the contracts. And so what happens here is you pass in the root event and the segment events to indicate, well, look, these are the contracts that, or the root event will say whether it should be, everything should be committed or discarded. And the segment events are going to say which contracts should be unlocked or locked now, and the provisional updates applied or discarded. So when you're actually executing, these cross-function blockchain function calls, like in your business logic, what you're doing is you've got to actually call back into the cross-blockchain control contract and say, look, this is the actual values that have been given. Do they match what you expected? And so what happens is, all right, I've just gone a bit off track here. Yeah, I'll go to this and I'll go back to contract blocking. So what happens is you fire in your segment or your root into that cross-blockchain control contract. You check that the signatures are okay, and that you trust the values that you're being given, the events that you're being given, for instance, the start event. And then you call the application entry function call. So if you're in a segment, you'll be in a certain part of the overall call graph. And so you'll execute that. And then there might also be some non-lockable business contracts that you might want to call as well. So they might not be doing any updates. But then the ones that are doing updates, I'll call into their delegated lockable contract storage, and they'll be able to use that to do provisional updates and also read back values. And so if the contract gets locked, then it'll indicate into the cross-blockchain control contract, hey, this contract's being locked. If whilst the business logic is executing, there are some cross-blockchain calls, it'll call back in and say, hey, this was the function call that I've been called with, and these are the parameters. Are they the ones that were expected? And so the cross-blockchain control contract has got the whole call graph, so it knows what should be called and in what order and with what parameter values. So that is how it works and how it can make sure everything's executing correctly. And so going backwards a bit, so we talked about contract locking. And so what happens is you need to be able to lock your data and then have the contract storage locked. And then if then you wait for your signaling transaction to unlock the contract and either commit or discard the updates. And so the locking model is super simple. It's fail if locked. And it means though that, you've got to be careful about execution order, and essentially you want to be making sure that you're just reading or then writing. And so, yeah, can be a bit tricky. And so to make it simple, there's a lockable storage wrapper contract, which lets you do simple stuff like you can see here, say set stock. You're essentially setting a map value nice and easily. Or if you want to set, say, just a uint 256, then it's nice and simple and just a very simple call. So there are parallel and serial execution engines. So if you execute everything in parallel, it happens quicker, but alternatively, you can use a serial execution engine. And there are various scenarios where serial might be better than parallel. It allows you to do slightly different things. So implementation. it uses, so this code overall, it uses a slightly modified version of Web3j, which I'm going to put the pull request in for sometime soon, Connor. And in fact, I'm actually in the last day or two been getting ready to do it. The enhancement to Web3j just allows you to determine the RLP encoding of a function call. So essentially it provides new function call hooks. So at the moment, the code is written in Java for the actual library that uses the Solidity code. You can see that it uses a fair bit of gas at the moment. I'm sure that that's going to be at least halved pretty soon, because we're just about to put effort into that. And I know I have some very good ideas on how to reduce the gas dramatically. Latency is another big thing. And so, for that trade finance scenario where you were going across all those blockchains, if you were using a parallel execution engine, you could get the whole thing done in essentially 5 latency periods for when blocks become final. So if you had instant finality, there would be 5 blocks. So there's been a whole heap of security analysis, which you could look at in the archive paper. There's a stack of future work to be done. Yeah, I'm in the middle of doing it, and we're in the middle of getting people on board to help with that as well. And in summary, this GPACT protocol is all about atomic cross-chain transactions, atomic cross-blockchain function calls. It works on any EVM-based blockchain at the moment, but it should be able to work on any blockchain at all that supports contracts and events. And that is me done. And so I should stop sharing and say, are there any questions?
Thanks, Peter. I'll just kick things off just with, it's more just about, I suppose, stepping back. And I think from what you're saying, the broader goal here really is that already we have a number of different Ethereum networks, like things like the POA network, all these different companies that are kind of spinning up their own blockchain networks that are actually using Ethereum behind the scenes, obviously the public mainnet and so on. And I guess this is kind of, in the nearer term anyway, this is kind of the glue to kind of enable this sort of hybrid environment where applications can run across like all of these in a more seamless manner, right?
Yeah, and for that, I think it's more than just in the near term. I think these sorts of protocols like the one I've created are going to be with us for a very long time. I think we're going to have, and I think that we're going to have more and more blockchains. So we're going to need a lot more of this cross-blockchain blockchain interoperability. I think it's a big thing now, and I think it's going to become bigger and bigger. And if people are thinking about finding jobs, I'd say cross-blockchain interoperability.
Yeah, and you've obviously seen the space evolve a lot in the last few years with the time you've spent on this. And do you think, though, the approach you're taking, you'd expand it to look more generally at Ethereum to non-Ethereum compatible chains as well? Because there's obviously a myriad of different platforms out there, but do you feel like that's the direction that it might go down the line, or is it kind of too early?
No, we've had user requirements to have across multiple blockchains. So there was a consortium, and their concern was vendor lock-in, where they're deeming Ethereum to be one ecosystem, and so they wanted to have across Corda and Fabric, as well as Ethereum, which anyway, I mean, but at the end of the day, if you've got a paying customer who says we want it to, we want to have the ability to have our business logic across multiple chains. I think the other thing to think about is that people have deployed stuff. So back in 2017, 2018, this whole cross-blockchain communication thing was a nice concept, but it didn't really matter too much because people hadn't deployed stuff. But now people have actually deployed stuff. They don't want to, they don't want to turn their blockchain off to join your blockchain. They want to keep their own blockchain because they've got real data on it.
Yeah, absolutely. And with the layer 2 scaling technologies, I mean, of course, what they're trying to achieve is slightly different, but and presumably there is some crossover there in terms of the approaches potentially some of those teams are taking, and the sort of work here, because ultimately there's you're finding ways to really well, it's bridging blockchains, but it is a slightly different use case, but there's presumably some crossover with the parts of the approaches.
Yeah, I think there is. They're cross-shard and cross-roll-up. It's a simpler problem to solve, but it's still in the same space, definitely.
If people want to start sort of playing around with it and familiarizing themselves with it, of course you mentioned the GitHub repos, but are there like specific areas that you think are great starting points?
So there are some examples in there that help to illustrate. So that trade finance example is actually there, and so you could use that. And at the moment, it's designed to all run on your laptop. So, which it could run on mainnet and, across test nets and stuff, but right at the moment, it could be just run on your local blockchain, on your local laptop. And it's reasonably simple setup. There is, README files, so that would help people to understand. One of the things that I'm going to be working on in the near future is a token bridge. So so essentially a ERC20 and ERC721 token bridge using the technology. It's obviously a simple use case, but one that people might be interested in having available as an implementation. Well, another interesting use case, actually, in the Ethereum Engineering Group meetup, we've got a guy from Brown University who's going to be talking about distributed automatic market makers, so AMMs, and so having a network of them. And so I'm not sure, but I'm pretty sure that things like that will require business logic across blockchains, because you're going to have different blockchains doing stuff. And rather than just being value transfer, you're actually going to want to have function calls. And so complicated stuff like that might be an example where it might be quite useful.
Thank you so much, Peter. It's really awesome to hear how far the work's come. And someone popped in I think definitely it's really cool to hear as well that there's some bridges coming as well, because then it really gets the stuff out there, and people can start working on top of this. Just to talk about our next meetup, which will be happening next month. We have John Whelan, who's Managing Director of Digital Assets at Banco Santander, one of the world's largest banks. He's also the chairman of the Enterprise Ethereum Alliance as well. So really looking forward to having John speaking. I also recently started a podcast as well, which goes out every week, where I discuss just the main things that are happening across, crypto, enterprise blockchain, DeFi, and the NFT markets. And that's available as podcast, also YouTube, it's a video, and you can see that on our Web3 Labs channel. And then there's a Clubhouse session as well, where we just discuss the items that have come up that week.